All right, so an Eulerian circuit is a circuit in a graph that contains every edge and vertex. Likewise, an Eulerian trail is a trail that contains every edge and vertex. So the name comes from an old problem that was solved by Euler called the Königsberg Bridge problem. So in the town of Königsberg, there are 7 bridges going across parts of a river connecting 4 different land masses, and the problem, or the game with the children, was to see if it was possible to cross every bridge exactly once and end up where you started. And as we'll see, you can actually prove that this is impossible. And Euler's proof that it's impossible is what eventually led to the concept of an Eulerian circuit. So we're going to refer to a graph as being Eulerian if it has an Eulerian circuit, and semi-Eulerian if it has an Eulerian trail. So let's look at this graph that we've seen before. If you go from B to A, then A to C, then C to D, to H, to B, then down to E, then over to G, then over to F, then back to E, then back to the D, and then back, we see that we end up where we had started, and we crossed every edge exactly once. So this graph is Eulerian. On the other hand, if we remove the vertex H from our graph, then that gets removed from our trail. And it turns out that, as we'll see later in lecture, you cannot actually find an Euler circuit anymore. But you can still find an Euler path, namely doing almost the same route we already did. You go from B to A to C to D, but now you see you can't go up to H anymore. So we just go down to E, then to G, F, E, B, and then D. And so as you can see, we cross every edge once, but we don't end up where we had started, so this isn't a circuit. So this graph where we've removed H is semi-Eulerian. Now let's look at one more example, and let's remove the vertex D and pretend it doesn't exist, or its edges. Now for this graph, I claim it's not actually possible to find an Euler path. And part of the reason why is because we see vertex C and vertex H both have degree 1. And so, there's only one way to enter those vertices, so these would have to be our starting and ending points. And so then we see that, you have to get through every edge. So in particular, somewhere along the route going from C to H or vice versa, we'd have to go down this path to E. But then we see that we're stuck because we can loop back around, but then we end at E. And so we fail to end at the 2 vertices we need to end at. So this graph is not Eulerian and is not semi-Eulerian. So it turns out that we can exactly classify which graphs are Eulerian. A graph is Eulerian if it is connected, which seems like at least one condition you must have, because if your graph is not connected, then you can't actually create a trail going through every vertex. The other requirement is that the degree of every vertex is even. So for the proof, first suppose that G is Eulerian, which means we have an Euler circuit. I'm going to denote the vertices of the Euler circuit as V0 through Vn. And so given any pair of vertices in our graph, x has to be Vi and y has to be Vj for some I and j. If we suppose for a moment that I is strictly less than j, then if you follow the circuit starting at Vi plus 1 to Vj, then it turns out you get an xy walk. And as established previously, if you have an xy walk, then you have an xy path. And so particular, given any 2 pairs of vertices, they are connected by a path in an Eulerian graph, so our graph must be connected. So that clears up the first condition. Now we need to show that if the graph is Eulerian, then the degree of every vertex is even. So take a vertex, V. If V appears on our circuit as Vi, then we see that vi minus 1 and vi are adjacent, and vi and vi plus 1 are both adjacent, so we get two edges. In particular, every time our vertex appears in our circuit, we find two distinct edges incident to it. And since every edge has to appear on the walk exactly once, this tells us that each of our edges must be incident to V must be appearing in pairs. And that tells us there are an even number of edges incident to V, and that means the degree of the vertex is even. So that satisfies one direction. If you have an Eulerian graph, it's connected and the degree of every vertex is even. Now we need to show the other direction. Given a graph satisfying these two properties, it must have an Eulerian circuit. To prove that, we will use induction on the number of edges. I'm going to skip the base case, but the base case would be your graph has no edges. We're assuming our graph is going to be connected and the degree of every vertex is even. And so if your graph is connected and you have no edges, your graph has only one vertex. And the vertex by itself is an Eulerian circuit. So we're going to focus on cases where we have more than one edge. So since we have a positive number of edges and our graph is connected, we can argue that the degree of every vertex has to be positive. Because if the degree is 0, then you have an isolated vertex and your graph is not connected. And so the degree of every vertex has to be positive and even, so the degree of every vertex is at least 2. By a lemma established in a previous video, this implies that our graph contains at least a cycle. Now the overall proof strategy is going to be to delete that cycle, use induction to get an Euler circuit on each of the components, and then explain how to combine those circuits together with the cycle to get a circuit in the original graph. So in order to apply induction, you need to point out that for every vertex in your graph, it's going to be either not on C at all, so it has no edges incident to C, or if it appears on C, it has exactly 2 edges in C. So in particular, if we remove those 2 edges, the degree changes by exactly 2, or 0. So in G prime, the graph obtained by deleting the edges of the cycle, the degree of every vertex is even. Unfortunately, we can't guarantee that the graph is connected. But what we can do is apply this induction hypothesis to each of the components of G prime. So in each component of G prime, the vertices have even degree and the components are connected. And so by induction, each component has an Euler circuit. Then the argument is to start by following the cycle you started with, and then each time you enter a new component, you follow the Euler circuit that you know exists for that component. And then once you've finished that circuit, you go back to following C. I'll illustrate that step in the proof with an example. Here's the graph we've been working with. We see a cycle exists, A, B, E, D, C, A. We delete the edges of that cycle, and we end up with this graph. We see that there are 4 components, and the degrees of each vertex in the components are even. And so by induction, there has to exist Euler circuits of each of these graphs. So B to H to I to B would be an Euler circuit for this graph. F, E, G, F would be an Euler circuit for this graph. And then so what is our strategy? We take our starting point in our original cycle, A, then we follow it until we hit B. Then we see B is in this component, so I follow the Euler circuit we found for this component, which was BHIB. Now I'm back at B again, and I can start following the original red cycle. So the next vertex is E. But now I'm in this component, so then I start at E, and I follow the circuit around. It's GFE. And now I'm back at E again, and I see I can finish off my cycle by going to D, C, and back to A. Now to show that this result is in fact an Euler circuit, we notice that every edge in your graph either appears on your cycle in which case it only appears on our walk exactly once. Or if it's not on the cycle, it's in G prime, which means it's in one of these components. And by induction, then it only appears on one of these circuits exactly once. And so we're guaranteed that we traverse every edge exactly once. And by construction, we end up exactly where we started. So it is a circuit. To end this video, I will point out that there's a similar result. So a graph is semi-Eulerian or has an Euler trail if and only if G is connected and the graph has exactly two vertices of odd degree. So I remember in high school there's always the challenge to draw this house with a cross going across the middle of it without and ending where you start without lifting up your pencil. And you can see using graph theory that the degrees are almost all even except these two. So that tells you it's not possible by the previous theorem, but it does tell you it is possible to at least trace out every edge if you're allowed to end at a different endpoint, and you're fine. On the other hand, looking at the graph that appears for the Königsberg bridge problem, we see that we have vertices of only odd degrees, and so we're not even guaranteed that an Euler trail exists. We know it doesn't exist.